So today I would like to present you my latest publication called Learning Cost-Effective Sampling Strategies for Empirical Performance Modeling. And basically it's about trying to improve the cost of the performance modeling process. So as you may know, or many of you will know, scaling code to bigger machines is not easy. And there can be a lot of unpleasant surprises while doing so. So your code may work fine on a small machine. There's only little communication overhead, and but when you're trying to scale it to a bigger machine, suddenly you have a huge communication overhead. That's not always like directly you can see this when you program it on a small machine, and it's hard to tell if your code is scaling. That's why we're using performance models. So what is a performance model? Basically, it's just a formula that expresses relevant performance metrics as a function of one or more execution parameters. Here you can see just a easy example with the number of processes as one of these parameters, and then modeling the runtime as the performance metric. So in this case, the runtime would be increasing with this function depending on the number of processes. However, you can create these performance models manual, but usually it's very hard to cover your entire code, cover all of the kernels, and it's of course really difficult to do so, and it takes a lot of time. So that's where like automatic empirical performance modeling comes in, and our tool ExtraP. So what ExtraP basically can do is you can instrument your code. So let's say all of your different methods, the main, foo, bar, compute, and then run it on a small scale, make small scale experiments on a, and then using these small scale experiments, we can use ExtraP to create human readable performance models like the one you can see here. So again, cover like expressing the performance of your program as these parameters, for example, the number of processes, and can do that automatically. So how we do this is actually pretty simple. We're trying to find the best single parameter model by combining different hypotheses we construct. So for example, we have we want to model just one parameter. Then we construct here these function hypotheses with some constants and our parameter. And now we use different types of polynomials and logarithms, and also combining them, as you can see here. And then we basically try all of these hypotheses and see which one fits our data best. And that's in the end our best performance model. Of course, there's more heuristics involved to speed up the process, so we don't need to explore the entire search space, but in a simplified form, that's what ExtraP is doing. And then in the end, we can, for example, model the number of time, the runtime, or like the flops, as you can see here, as the parameters n for problem size may be, and the number of processes, for example. But still there's a problem, and the problem is, or was, the number of measurement points ExtraP required to do this automatic modeling. So before ExtraP required at least, as you can see here, 5 to the power m plus 1 experiments, where m is the number of parameters. So this means if we want to model our program just one parameter, so let's say the number of processes, we need at least 5 small-scale experiments for that. But if we want to model 2 parameters, as in the example here with the number of processes and the problem size, then we already need the 25 small-scale experiments. As you can see, this number rises quite quickly. So for 3, we would need 125, and then for 4, like over 600. And in this case, we're not even considering taking repetitions of these measurements to take care of some noise we also might have on the cluster. So if we also consider we might take 5 repetitions or so of each experiment, then we quickly need maybe 1,000 measurements or more for like to model a 3-parameter application. Another problem that comes in is here, it's not always possible to model this full matrix of points. So the example here tries to show that for some applications, it might be the case that if your problem size gets bigger and your number of processes is really small, you might run out of memory actually on your nodes. And going in the other direction, if you have a large number of processes, but your problem size is very small, then the runtime will be so short that maybe you will just measure the system jitter. So it's not always possible actually to cover this full matrix, and this was a problem before for ExtraP. So for some applications where we couldn't measure this full matrix, we were not able to actually create performance models for them. So the idea now that we had was why not just use less points, and for example, it should be enough to use 5 points each for each parameter. So let's say we're using this black round dots here for the number of processes. So we're just using these 5 points to model a function for the number of processes. And then after that, we can use this rectangular, gray rectangles here to model the problem size as a function. And then we may be able to combine these functions to create a performance model that expresses both of the parameters. And then maybe we also might be able to use some additional points, choose some of them to increase the accuracy. But the problem now is how we're going to choose these points. And would it be best to choose this line of 5 points for the number of processes, or maybe it would be better to choose this line of points? To solve this question, we took some inspiration from machine learning, more from AI, and this, for example, AlphaGo example, or like the solving the chess game. So in the end, what they're doing is also exploring the exploration space of the game, of the board in this case. And instead of just trying to calculate each possible move, they're trying to do pattern recognition and then extract some rules what should be the next best move in the current situation. And so one idea that we could apply from this would be basically also create a reinforcement learning agent that basically explores the environment for us and not just tries all of the combinations, because as I told you before, like if we keep increasing the number of parameters that we want to model, the space, basically the number of combinations increases exponentially. So for 2 or 3 parameters, it might be still possible to actually calculate what are the best choices of measurement points. But if you keep increasing the number of parameters, it's not possible anymore. So instead, a reinforcement learning agent can actually learn which points should be chosen in a certain situation. And based on this, we created our own reinforcement learning agent to solve this problem. So what we did basically is we created a function generator that creates artificial performance functions with different number of parameters, with different types of parameters. Some of them maybe use floating point values, some of them integer to mimic real life parameters like number of processes or the problem size or other floating point precision parameters for computation, etc. And we also added a noise module to this function generator to mimic the noise it may occur on a cluster. And what we do then is generate a number of synthetic functions and feed them into our reinforcement learning agent. Then the reinforcement learning agent, based on this input, he will decide which measurement points should be selected for the modeling process. Then we use the selected measurement points as input to ExtraP and create an empirical performance model using ExtraP. Of course, then we have our prediction for the performance and can evaluate that against the ground truth that, of course, we get from the function generator. And then in the end, we can give the reinforcement learning agent feedback if he choose, basically, if you choose a good combination of points that led to high accuracy performance model, or if the combination of points was really bad and we couldn't get like a good accuracy. So this simplified version of some training examples, as you can see here, that actually works, and the accuracy is increasing while over the training epochs, while at the same time the cost of the modeling process is decreasing. One thing you might ask is, if you take a look at the axis of these plots, why the reward and the cost just moves between, for example, the cost just move between 4 and 12%. Why not 100%, you might ask? So the point is we made some restrictions to the agent. So he cannot choose any arbitrary point, because in reality, this wouldn't make sense, as ExtraP requires at least 5 points for measuring. So as you may remember, we need at least one line of these 5 points per parameter. So that's why it doesn't make sense to let the agent choose arbitrary number of points. Of course, this also introduces makes the problem more simple for the agent. That's why he's able to acquire right from the start, basically, just to use only 12% of the budget. Then you can also plot basically the selection of the different measurement points in kind of a three-dimensional heat map, what I did here. So here you can see this example with 3 parameters. And now if you plot the relative number of selections that the agents did for the different measurement points, let's say over 100,000 synthetic generated performance functions, then you can see actually in more than 95% of the cases, he will always choose these points that are highlighted in red here. And as you can see, the other points are basically never chosen. So what does that mean for us? Basically, this means that in this case, it was always fine to choose the points with the lowest cost, and we still are able to get a very high accuracy performance models with these cheapest points actually. And it also shows that it's perfectly fine just to use these 5 points per parameter for modeling. And in maybe just 3% of the cases, we needed an additional point for modeling. In the next step, we simplified this using heuristic, basically also trying to provide a guideline for the user on how and which measurement points he should choose when conducting the small-scale experiments. So basically, we're saying we're going to make a trade-off between your cost, your budget that you have for modeling, and the modeling accuracy. So first of all, we will measure the minimum number of points that is required for modeling with ExtraP. Then we will create the first performance model using ExtraP, and then we can check, do we still have budget left or not? And if we still have budget, we can gather additional measurement points and evaluate our model again to see if we were able to increase the accuracy. If we're not able to increase the accuracy after taking, let's say, 3 or 4 additional points, it is very, very likely that we will not be able to increase the accuracy if we add even like 20 more points. And on the other side, of course, if we run out of budget, we also done and we have our final model. So now, of course, we evaluated our methodology to see which accuracy we will get depending on the number of points we choose and if this heuristic we formulated really works. So therefore, we evaluate over 100,000 synthetically functions with different amounts of noise, different number of parameters, and different number of repetitions to counter noise. And then what we do is we basically take 5 measurement points. So this is just an example for one parameter. So in this case, we take 5 measurement points for modeling, and we take 1 additional point for evaluation. And based on these 5 points, we will create this our model. And on this point, then we will evaluate it. And the metric we use for evaluation is basically we create different buckets here, as you can see. So 4 different buckets. So first of all, we check if it's inside -5 or +5% of the actual value, and then 10, 15, and 20%. So if we take a look at the evaluation, you can, of course, see for one parameter, there's no difference, as anyway, we always need these 5 different points. However, for 2 parameters, we start to see difference. As you can see, usually we would require 25 points before. It is 100% of the budget. Now, when we're decreasing the number of points, we can also see that the accuracy decreases. But we can still achieve pretty high accuracy for that. So as you can see, 9 points is basically the minimum that we need for 2 parameters. So we do not necessarily need 10 points. As I said before, we need 5 points per parameter, but actually they can also overlap. So 9 are actually sufficient. And in this case, you can see the number of repetitions doesn't really matter, but we're still able to achieve like kind of 70% of the previous accuracy. But it's just 12% of the budget on the other hand. This gets more interesting if we increase the number of parameters, of course. As you can see here again with our full matrix of points, the accuracy is very high of our modeling approach. And of course, we will get less accurate results if we just use the minimal number of points. For 3 parameters would be 13 points. You see, we get only around like 60–65%. But also we have to consider we're just using 1.7% of the previous cost of the full matrix. And as you can see, we can add up to 75 points, and they cost just 11%, and we almost get the same accuracy as the previous model. So as you might see, 75% just cost 11% of the cost of the full matrix. And that is because not each point has the same cost, basically. So if we go back to this matrix view, basically, this point here in the bottom left will have the cheapest cost in most places. So we basically define cost as the runtime times the number of processes. So this means in that case, this point will have the lowest cost. However, the cost is of course also increasing with the problem size, but less than with the number of processes. So in general, this point up here in the top right will be the most expensive point. So that's why you're actually able to take like 75% of the matrix, take all of these points, but they are still cheaper than this point in the top right corner. And then this results basically in this chart here, that we can take up to 75 points just using 11% of the budget and basically get very high accuracy results. For 4 parameters, this is like even more drastic. As you can see, the minimum number of points now just use like not even 1% of the budget anymore. And with only like 4%, we can get same accuracy as before. We also analyze 4 parameters for different noise bands, and you can see the smaller the noise, of course, the more accurate our model. And you can also see if you have less noise on the measurements, of course, we can reduce the number of the number of measurement points that we need even more. So in this case, we can also only use 125 maybe and get the same accuracy as we got before, like with the full matrix even. Additionally, we did some case studies. We did 3 different case studies. First of all, fastest, which is like a fluid simulation from developed by a group of TU Darmstadt. And for fastest, we were actually able to achieve like 70% decrease in cost, and basically only have an additional prediction error of 2%. So we were able to decrease the cost for modeling by 70%, but only adding 2% prediction error. Then we also analyzed Kripke. And for Kripke, which is 3 parameter simulation, fastest was only 2 parameters, we can decrease the cost even by 99%. And in the end, we have a modeling error of 39%. However, of course, that's only if our main goal would be cost reduction, because 39% prediction error might be quite high, but here we just want to show like what's actually possible. So of course, if we maybe take still only reduction by 90% of the budget, we can achieve prediction errors of just like around 5%. Relearn, another application from TU Darmstadt, simulating neurons in the connectivity of neurons in the brain. We were able to reduce the cost for modeling this application by 85%, and in the end we just have around 11% prediction error at our evaluation points. So overall, we were able to achieve like a large decrease in modeling cost for all of the case studies, and we can basically retrain the model accuracy of the old approach while doing this reduction. In conclusion, we're able to achieve like an average cost reduction of about 85%, but of course it depends on the application, and while still retaining 90% of the model accuracy in average. And now we just require a polynomial number of measurements instead of this exponentially increasing number. And we have also a more flexible experiment design basically for conducting the measurements. As I explained before, so in cases where you would run out of memory or you get problem measuring system jitter because your problem size and the number of processes would be too large, you can just ignore these measurement points and take them now more flexibly and still conduct and create your performance models using ExtraP.